In the world of big data, Apache Spark stands out as a powerful framework that allows for processing large datasets rapidly and efficiently. Whether you're dealing with batch processing or stream processing, Spark makes handling data more convenient compared to traditional methods. In this tutorial, we're going to explore what exactly Spark is, why it's so important in today's data landscape, and how it actually functions. So, buckle up and let's dive in. First off, let's talk about the key features of Spark. It's designed for speed and, it achieves this by relying on in-memory computation, which is a fancy way of saying it keeps data in RAM instead of reading from disk all the time. Now that can significantly speed up processes, especially when you're working with massive datasets. But what else? Well, Spark also handles complex analytics like machine learning and graph processing quite well. Now, why is this important? Well, in our data-driven world, making decisions quickly and accurately is key, and Spark gives us that edge. All right, let's get into how Spark works. Imagine you're streaming data from various sources. Spark can efficiently manage that in real time, allowing for immediate insights. And with its user-friendly APIs, both in Python and Scala, you'll find it versatile for all types of developers. So, as we move forward, keep these aspects in mind: speed, versatility, and the ability to analyze vast amounts of data in real time. All right, let's explore Spark's architecture before we wrap up our introduction. It's made of several components, including the driver, cluster manager, and executors, which work together seamlessly to process data. Wow, that's a lot to unpack. But don't worry, we're going to break it all down in upcoming videos. So stay tuned and, let's continue our journey through the powerful world of Apache Spark. Now, let's see how we can implement the creation of a Spark session in Python using PySpark. We start by importing the Spark session class from the PySpark.sql module, which is really essential for utilizing Spark's SQL capabilities and DataFrame API. The next step is to use the builder pattern to configure and create our Spark session. This is done by calling the builder method, which allows us to define various settings for our session. In this case, we specify master local/star, which tells Spark to run in local mode and utilize all available cores on our machine. This configuration is just ideal for development and testing because it provides ample processing power without the need for a full cluster setup. We also assign an application name with appname introduction to Spark, which gives context to our job and makes it identifiable in resource monitoring tools. Slight pause. Finally, we invoke getOrCreate to either retrieve the existing Spark session or create a new one if it doesn't already exist. This really sets the stage for all subsequent data processing asks within Spark. Now, let's dive into how we can load our CSV file into a Spark data frame. This is a crucial step in our data processing workflow. We do this using a command that reads the CSV file, making sure to specify the file name along with two really important parameters: header equals true and infer schema equals true. So, what does header equals true do? Well, it tells Spark that the first row of our CSV file has the names of the columns, which, let me tell you, is super useful. This ensures that our data frame comes equipped with proper column labels that match our data set. Now, on to infer schema equals true. This little gem allows Spark to automatically figure out and assign the correct data types for each column based on the values in that CSV. No more headaches from manually defining the schema, making our lives a lot easier, right? After we've loaded the data successfully, we can peek into our shiny new data frame by simply calling the show function. This function gives us a quick glance at the first 20 rows, allowing us to verify that everything's loaded correctly and that our data is primed for further analysis. Now, let's see how we can filter our data frame to find specific user segments. In our code, we're going to create a variable called USA over 30, which will store a filtered version of our data frame, df. We use the filter method to apply two conditions. First, we select users who are older than 30 years, and second, we make sure they reside in the USA. This really showcases the power of Spark's DataFrame API, allowing us to effortlessly manipulate large datasets with such clear and expressive syntax. Next, we'll call the count method on this filtered data frame to get the total number of users meeting our criteria, and we'll save that count in a variable called USA over 30 count. This highlights how we can aggregate data to gain insights rather than just scrolling through raw records. Finally, we'll use the print function to output the number of users over 30 from the USA, demonstrating just how simple it is to perform these operations, making data analysis both straightforward and efficient. Now, let's implement the aggregation functionality in Spark to find average values. We'll create another variable, average age per country, which groups the data frame by the country column. By using the ag method with an aggregation function, specifically average, on the age column, we can compute the average age of users for each country. This powerful feature supports deeper analysis of our data. When we call show, it displays the results clearly, showing how Spark simplifies these complex data operations. Now, let's see how we can implement a Spark streaming application that reads text data from a socket. We begin by creating a Spark session, which is crucial for any Spark application, acting as the entry point for all Spark functionality. In our case, we're configuring it specifically for a streaming example. Next up, we set up a data frame that represents the incoming stream of data. Here, we specify the source format as socket and provide the host and port number where our data will be streamed from. So, we've chosen localhost on port 999. This setup will allow us to capture any text data sent to that port. Now, let's focus on how we process this incoming data. After establishing our stream, we can leverage Spark's powerful built-in functions. We're going to split each line into individual words using the select method combined with explode and split, so we can handle each word separately. Following that, we perform a group by operation on the words to calculate their counts, which gives us a data frame that shows each unique word alongside its occurrence count. Finally, we initiate a streaming query to output these counts in real time to the console, providing immediate feedback about the stream data. This setup effectively illustrates how Spark streaming can be utilized for processing real-time data. Now, let's implement a simple linear regression model using Spark's MLlib. First, we import the linear regression class. This part is key because it provides the tools necessary for fitting our linear regression model, which is quite powerful, right? Next, we define our sample dataset, consisting of pairs of independent and dependent variables. In this case, x is our independent variable and y is our dependent variable. And we represent this data as a list of tuples. We also specify the column names, which helps Spark understand the structure of our data frame. Now, we create a data frame using the createData function method of our Spark session, passing in our data and column names. This data frame will serve as the input for our model training. Following that, we instantiate the linear regression model by specifying which columns will serve as features and labels. The features call parameter indicates which column contains our independent variable, x, while the label call parameter specifies the dependent variable, y. Now that our model is set up, we can fit it to our training data using the fit method. This step is crucial as it enables the model to learn the relationship between x and y. Finally, we print out the coefficients and intercept of the trained model. These values tell us how x influences y in our linear regression context. This simple example showcases the power of Spark's MLlib to handle machine learning tasks efficiently. Now, let's implement caching in our Spark job to enhance performance. Caching is a strategy that allows us to save the intermediate data frame in memory. And this can significantly reduce processing time for subsequent operations on the same data frame. By using the cache method, we instruct Spark to keep this data frame in memory, making future actions that reference it much quicker, as they can bypass those time-consuming disk I/O operations. Now, this optimization is particularly beneficial when we're working with iterative computations, or when the data frame will be accessed multiple times in your workflow. However, it's essential to consider the trade-offs involved. While caching can improve performance, it may also lead to increased memory usage. So, it's crucial to monitor memory consumption and only cache data frames when justified by the performance gain. Always ensure that you strike a balance that suits your workload and available resources. By integrating this simple but powerful feature, you can make your data processing tasks in Spark more efficient and responsive. Short pause. In summary, Apache Spark has completely transformed how we handle big data processing. Its incredible speed, flexibility, and robust processing capabilities really make it a go-to framework in any data engineering toolkit. Whether you're tackling batch processing, diving into real-time analytics, or venturing into machine learning, Spark offers a powerful solution that really stands out. So, thank you for tuning in. And don't forget to explore Spark even deeper, especially as you dive into those real-world applications.